Yeah, draw the circuit first, and then we'll look at how it works. This example is going to cover a simpler version. It's going to do a 2-bit A to D converter. By 2-bit means it can only accept 2 bits, 2 places. So it only can go up to 3, 0, 1 to 3. And if you want to go 10-bit and all, you need to add more logic gates and flip-flops, as I'll show you. So 2-bit A to D converter. So here is the circuit. Okay, so these are 3 resistors in series. We'll pull them, well, we'll connect these wires to 3 logic gates. Sorry, not logic gates, my bad. We'll connect it to 3 comparators. So these are op amps. And then this is the input. So connect it here. So the dot here would represent the connection. So if you see a cross line, doesn't mean it's connected unless I show it with a dot. Correct. It can go all the way here. So this will then go to 3 D flip-flops. So D, this is the clock. So let's call this one D, and clock is fine. D, and clock. This is going to be the negative, positive, negative, positive, negative, positive. The outputs of these are change this line type. Yeah, there's more circuitry, but we'll get to that. So this is, let's say, G2, G1, G0, and then let me call these Q, Q, Q. And then there's one more piece, which is, this is our Vmax. This is a voltage which you supply, Vmin. And then these are reference voltages which we'll be using, V2, V1, and V0. Okay, so let's see how this works. Okay, so Vmax and Vmin are controlled by the designer. These are basically set. These are set in advance. That is, you'll connect it to some kind of a power supply, which will supply Vmax, Vmin. They'll be constant voltages. Vin is your input. This is the input we are trying to convert to binary numbers. So let's say that if we had 10 volt, we want 10 volt to correspond to the number 10. So that's what Vin would be, and 10 would show up in G2, G1, G0. In this case, since it's 2-bit, we can only go count from 0 all the way to 3. So you can only go up to 3. So let's say we want 10 volts to be 3, then G2, G1, G0 would be appropriate binary numbers. Okay, now before we get started, this is something which we can do because we can figure out what voltage V2, V1, V0 are. So these are just reference voltages. They are not, they are a function of how we connect Vmax and Vmin. So you can see that from this figure, you can see that the voltage drop across Vmax minus Vmin will be the current flowing through this branch whatever that is, times the resistance. So there are 4 resistors, they're all in series. So we will have, oh my God. Okay, so it'll be I times 4R because there are 4 resistors. Similarly, we can write V2 or Vmax minus V2. So this is the voltage drop across these two. It will simply be I times R. So clearly we can simplify this. We're going to move Vmax minus V2 up. Vmax minus V2 is 1/4 Vmax minus Vmin divided by 4. And so what I'm going to do is, I'm just going to write this as V2 equals Vmax minus 1/4 delta V, where delta V is Vmax minus Vmin. Okay, so it's just simplification, nothing, it's very straightforward. Now, this is what we get if we do this, if we compute V2 as a function of Vmax and Vmin. You could do the same thing for V1 and V0. The only difference would be now, when you do Vmax minus Vmin, V1, it'll be the voltage drop across, or the, voltage drop across 2 resistors. So instead of having R here, you'll have 2R. And then same for V0 will be 3R. So you can write expressions similar to this. So I'll copy all these expressions down. So V2 will, something I wrote down in the earlier page, is Vmax minus delta V divided by 4. You can do the same thing for V1. It will be Vmax minus delta V divided by 2, because remember it was, instead of 1/4, it will be 2/4 because there are 2 resistors. And then we would have V0 will be Vmax minus 3/4 of delta V. So 1/4, 2/4, and 3/4. The 2/4 became half. Okay, so this is true no matter what Vmax or Vmin is. Now let's illustrate the working of this particular A to D converter using an example. So let's assume, so explanation on how this works. Okay, so let's assume we chose Vmax to be 16 volts. Right, 4 volts. And let's choose Vmin equal to 0, which is just saying that the lower one is connected to the ground. So Vmin is 0. Now from this formula, let's just call this something. Let's call this number 1. From 1, we can compute V2, V1, and V0. So Vmax is 4, Vmax minus Vmin, which is delta V. So delta V is Vmax minus Vmin divided by just that Vmax and Vmin. So if you do that, you'll see that V2 is 4 minus 1/4. So it will be 3. V2 would be 4 minus a half. Sorry, 4 minus 4 by 2. So it's going to be 2 volts. And then V, this is V1, and V0 would be 4 minus 3/4 of 4. So that will be 1 volt. Okay, so we have 3, 2, and 1. Let me just write it down in the figure. So we've computed V2, V1 as V2, V1, V0 as 3, 2, and 1. Let's put this in the figure. So this voltage for this particular example is 3, 2, and 1. So the comparator is going to compare against 3, 2, and 1. That's the key. Yes, that's the first thing. Okay, now let's go and dig a specific example. Okay, so let's say that let us say that okay, so here in this case we need to look at different combinations of Vin, right? Ultimately, what a goal is to figure out what sort of Vin will give us. We want to vary Vin in certain range and then see what G0, G1, G2 is. Now, in this case, I'm only going to let Vin vary from 0 to 4 volts because this is, as I said, 2-bit converter. It's only going to give us a range from 0 to 4 levels. So I'm just going to limit to 4 volts because also this comparator can only compare 3, 2, and 1. So we can't really compare any value which is greater than, anything greater than 3 will be the same. So if you put 5, 6, 7, you'll see that it doesn't really work because the maximum it can compare against is 3. So let's try different input values and see how this comparator works. So what I'll do is, when I send in 0 all the way to 4 volts, write that down here. So we'll vary this from 0 to 4 volts. Okay, so what will happen is, you can see that if this voltage is, let's say 0, if it's 0, then this comparator will say, when it compares 3 against 0, it's going to say that the output is going to be 0 because 3 is greater than 0. It'll compare 2 against 0, so the output would be 0. And here also we'll have 1 is greater than 0, so output would be 0. Okay, so that will be true for any input all the way from 0 to 0.99 volts, because 0.99 volts is less than 3, 2, and 1. Let me go ahead and try to create a table which will show how this works. So let's create a table. Okay, the table would have our input, and we just discussed what would happen if we send in 0 to 0.99. What we'll see is that G0, G1, G2. So all of them would be 0. When I say 0, it really means it's going to be off. It's not going to be on. Okay. Next, let's see what happens if we input anything between 1 and 1.99. Okay, so if you send let's take a value 1.5, for example. If you take 1.5 and send it through, since 1.5 is greater than 1, this one will go on 1 in the same color, 1 to 1.99. This will go 1 because 1.5 is greater than 1. Here it will be 0 because 2 is greater than 1.5, and here it will be 0. So the next output, anything between 1 to 1.99 will have the code. You can see G0 would be 1, G1 would be 0, G2 would be 0. So 1, 0, 0. So I have this backward in my notes. I have it like this, G2, G1, G0. So I said G0 would be 1, G1 would be 0, G2 would be 0. And this is, as I said, it's for 1 to 1.99. Okay, now let's see what happens if you send in 2.0 all the way to 2.99. So what will happen is, since 2 is greater than 1, this one will be 1. Since 2, it's 2.5 or 2.4 is greater than 2, this will be 1, and this would be 0. Okay, so 1, 1, 0. And then we can do the last case where if you send in anything above 3, so 3 to 3.99 or 3 to 4, then 3 is greater than 1, so this will be 1. 3 is greater than 2, so it will be 1. 3 is greater than 3, so this will be 1. So the output would be 1, 1, 1. So I'm just going to take these 4 cases and then put it in that table. So we said 2 to 2.99, 3 to 3.99 or 3 to 4. Output was 0, 1, 1, 1, 1, 1. Okay, so using these 3 comparators, we got 0, 0 all the way to 1, 1, 1. These numbers are different, which is good news, so I can somehow codify them. But the issue here is that they don't really correspond to 1, 2, 3, and 4. This number is 0, this number. So in decimal system, this number is 0. This is 1. This is 3, I think. And this is 1, 2, 4, 4, 6, 7, right? So 0, 1, 3, 7, but I don't really want 0, 1, 3, 7. I just need it to be 0, 1, 2, 3. So what we need to do is, in order to do that, something also I forgot to say is that this is the same as, this is the output of the comparator, but this is the same output as G2 because all the D flip-flop does is it basically takes whatever you get at D and outputs it at Q. So that was an assumption I made. I did not quite say it, but that D and Q will be the same for this D flip-flop. So what I need to do is I need a circuitry inside here, which will take inputs from G2, G1, and G0 and output just 2 numbers, B1 and B0. And this B1, B0 are the 2 bits I'm interested in, and they should codify 0 all the way to 3. So what I need is B1, B0 should be 0, 0, 1, 0, 1, 1, 1, 0, 1, 1. Now this is 0, 1, 2, and 3. Okay, so I need to take 3 bits, G2, G1, G0, and convert them to 2 bits. This is something we've done in the past with the truth table. If you're given a truth table, you can figure out the logic which goes into, in terms of gates, to convert one input to another input. So we talked about sum of products and products of sum. Yes, I'll not go through the process, but I have figured out there is a formula which can help you convert the G's to B's. This is what I get. P0 equals G0, G1 bar plus G2. And B1 is simply G1. Okay, so this is the logic which converts whatever I've written down here to the one on the right. So this one requires a NOT gate, an AND gate, and an OR gate, and this one is just outputting G1. So I can then, once I get this number 2, I can go back in the circuit and redraw whatever I want here. So G1 directly feeds into B1. So that will just try a different color for that. So this will just go, boom, that's it. Now for the other one, it's a bit more complicated. So I said it is G1, G0, G1 bar plus G2. So I take G0. I take G1, sorry, I take it through a inverter. And then I need to AND it with G0. So that's an AND. So I took care of this. Then I need to take G2. And I need to add it. So there'll be an OR gate. Okay, and this output is fed to B0. Okay, so that's some circuitry you need to come up with in order to convert G's to B's. Okay, so what we've been able to do is through, just summarize it here. So what we did here was we took op-amp, which is a comparator, and a D flip-flop in order to convert the analog signals to G's. And then the second step was, this is the step 1. The second step was using a logic gate to convert them to B1 and B0. So this gave us G1, G0, G1, G2. And this step gave us B0 and B1. So here is a way in which you can convert analog signals to digital signals just using op-amps, flip-flops, and logic gates. So now that we've done this, we can now look at this in comparison to what we had achieved with the other converter. So this was something I did last time. I had shown you a successive approximation converter. So we talked about this, and we saw that the way this works is it requires in this case, 4 steps. 1, 2, 3, and then there's another one on the next page, 4 steps. So using 4 steps, that is 4 time cycles, it was able to take the 6 volts and convert that to 0, 1, 1, 0. So this was 1 time step, another time step, third time. By time step, I mean the clocks is going, there's a clock, and that clock has to go cycle through 4 times to convert 4 bits of data. However, what we see with this converter is that since all these flip-flops are in parallel, the comparator op-amps in parallel, it can process the input voltage, all the bits in one shot. So even though it's with 2 bits, we were able to convert to B0 and B1 to just 1 clock cycle. So this clock cycle, which is here, you used only one single time step. And that was because we had added these flip-flops and op-amps in parallel. So now when you compare the circuitry, you see that there are more elements, more circuitry involved in the flash converter, which is this one, compared to the successive approximation counter, but it takes a lot shorter time to convert digital analog data to digital data. So to summarize, flash converter is efficient. It requires only one clock to process analog each analog data. This is the advantage. However, it requires many more components compared to successive approximation converter, which is a disadvantage. So you probably don't, even I've said this, I don't think you ever use successive approximation converters a whole lot, because it's just becoming so easy to put all these things in a single chip that you really don't need to worry with something which is that inefficient. Packaging more and more electronics is becoming easier and easier.